Welcome to part 2 of the video lecture for topic 15, substitution reactions of alcohols. And now this part, as I mentioned in part 1, strictly covers arrow pushing mechanisms for some of the new reactions that we haven't seen yet. And so the first new reaction that we need to look at is formation of sulfonate esters. So I'm going to start with the formation of tosylates and mesylates. Now, as we said, tosylates and mesylates are formed when we combine an alcohol with tosyl chloride or mesyl chloride. And so these two reactions are identical except for what is the other group hanging off of that sulfonate ester once it's made. And so for tosylates, right, R2 in our mechanism is going to be the toluene group, which has a structure that looks like this. And for mesylates, R2 is just going to be a methyl group coming off of that sulfur of our sulfonate ester. So we'll keep those in mind. And now, since the mechanism is the same otherwise, I'm just going to go ahead and keep these, right, in all my structures. I'm just going to write R2. You should know for tosylates, put the toluene in, and for mesylates, substitute that with the methyl. And so what does this reaction look like? So here again, we're going to start with a generic alcohol. We're going to have our sulfonyl chloride. Now keep in mind, whenever we do an arrow pushing mechanism, we want to use a Lewis structure, or more appropriately, I should say, a Lewis line structure. That means we need to show all of our electrons on our heteroatoms, right? We need to show formal charges when they're created. We need to be very thorough in our mechanisms so that we accurately convey what's occurring during the transformation. And so here now, we've got our alcohol here, and we have our sulfonyl chloride. Remember, R2 is toluene for a tosylate, and R2 is methyl for a sulfonate. And I'm going to keep my structures in one color, and I'm going to do all of my electron arrow pushing in a different color. So the first step that we have happen is an SN2 reaction where the oxygen of the alcohol acts as a nucleophile, attacking into the sulfur atom, simultaneously displacing chlorine. That takes us to our first intermediate, where we have R1 to our oxygen, right? We now have only one lone pair on this oxygen. That hydrogen is still bonded to it. That oxygen is now bonded to the sulfur of our sulfonyl chloride. We always want to have all of our electrons. And so this is our first intermediate. We have now here a positive charge on this oxygen, which means we have to have some negatively charged species to balance that charge out. And in our case, because we displaced that chloride, our negatively charged species is going to be a chlorine ion with all 8 of its electrons and a formal negative charge. At this point, our weak base will come along. Here now, I'm using pyridine. You could choose to use triethylamine instead. Either one of those is perfectly fine. I just happen to personally like pyridine a lot. And so pyridine now will serve as a weak base, deprotonate that oxonium that we generated to give our final products, which I'm going to draw down here below. And so now we have our sulfonate ester. We're always going to put in all of our electrons, even ones we don't use. Right? We see now we still have a chlorine anion. And we have protonated pyridine. And just in case you're wondering, yes, this is a favorable step. Remember that our oxoniums generally have a pKa of -2. Protonated pyridine has a pKa of 5. Higher pKa is favored in the equilibrium, right? So this situation down here, protonated pyridine, is going to be more favorable than the protonated sulfonate ester. And so these are our final products in the reaction. So that covers forming tosylates and mesylates. Next, let's take a look at how we form triflates. So for forming triflates, our overall reaction is going to seem very similar, but I want to do this arrow pushing separately because when making triflates we use triflic anhydride, we don't use a triflic chloride. And so I want to show you what that overall reaction looks like as well. So once again, we begin with our alcohol. This time now we use triflic anhydride. And we always want to put in our electrons. Yes, I know I'm skipping the electrons on my fluorine atom, but in interest in keeping this video lecture at a reasonable time frame, I'm just going to not draw out my fluorines explicitly. And so that you know, I won't expect you to draw out your fluorines explicitly for this reaction. You will be expected to draw the central portion explicitly, showing all atoms and all electrons. So our arrow pushing is very similar. Again, in our first step, right, oxygen acts as a nucleophile, attacking into one of the sulfurs. This time, however, instead of losing a chlorine ion, we lose, right, this entire piece over here. So now this sulfur-oxygen bond breaks, oxygen takes those electrons, and we get to our first intermediate. So here now we have, from our alcohol, we have that sulfur that we attacked into, and we have the CF3 group. Our oxygen still has a hydrogen, from our alcohol still has the hydrogen bonded to it. There's our lone pair. That oxygen takes a formal positive charge. And so since we have a positive charge on this side of at our starting materials, we were overall neutral. Here now, at our intermediate, we have a positive charge. There must be something to negatively charged to balance that out. And that was our sulfonate leaving group we had. So we need to show that charge balanced. And so that's where our negative charge to remain overall neutral is going to sit. From there, once again, we have a weak base, and this time, just to show the difference, I'm going to use triethylamine. Once again, you could have used pyridine here, 6 of one, half dozen of the other. And so now, excuse me, let's keep our arrow pushing in a different color so that we can distinguish our electron movement arrows. So now the lone pair on nitrogen of triethylamine deprotonates this oxonium. Electrons go to that oxygen atom, and we have our overall products formation of our triflate. So here now there's the R group from our alcohol, the oxygen from our alcohol, sulfur, 2 oxygens from our triflic anhydride. There's our CF3 group. We're going to go ahead, put in all of our electrons. And now all we have to do is draw our byproducts. We can see that we've protonated triethylamine. And we still have our counterion to balance out that positive charge on nitrogen with that sulfonate anion we generated in step 1. And we have formed our triflate, which is ready for substitution. And once again, we can confirm that this is the favored side of this acid-base equilibrium. And we're also going to remember to use equilibrium arrows, since that's an acid-base step, which I missed in the first mechanism. We should have equilibrium arrows anytime we do an acid-base step. But if we take a look, our acidic species here, pKa of about -2. Our conjugate acid from our base, pKa of about 10. This side of our equilibrium is favored. So we get to our triflate ester, which is ready now for substitution. Okay, so that covers forming sulfonate esters, right? Let's now move on and take a look at what happens when we use phosphorus tribromide or thionyl chloride to form an alkyl halide from an alcohol. So when we're working with phosphorus tribromide, right, again, this is only going to be for, I only expect you to know this for primary or secondary alcohols. You need to know the mechanism, but this reaction does work even for tertiary alcohols as well. But we're not going to get into that mechanism. Knowing primary and secondary is sufficient for me. All right, so I'm now actually not just going to use a generic alcohol, but I'm going to use a specific secondary alcohol right here, and let's draw out this OH bond explicitly, since we're going to be pushing arrows. And we'll draw out our phosphorus tribromide. With all of its electrons as well. All right, so now in the first step of this reaction, alcohol once again is going to serve as an electrophile. And in an SN2 step, whoops, let's stick with having our electron arrows be different than our reaction arrows. So in our first step, oxygen is going to act as a nucleophile, attack into the phosphorus SN2 to displace a bromide. This is going to give us our first intermediate, where now we have an oxonium, with our oxygen is also going to be bonded to phosphorus. We all now have this positive charge, so we have to have something to balance it. That's that bromide that fell off of PBr3. And finally, the bromide for our primary and secondary alcohols can now come and attack in SN2 at this electrophilic carbon, displacing that oxygen to give us our final products. We now have our bromide, our alkyl bromide, excuse me, right? Because this is an SN2 process, this product is formed with inversion of stereochemistry. And the byproduct that I need you to know is going to be phosphorus with 2 bromines and an OH group. Here now phosphorus only has 3 bonds, so it needs to have a lone pair on it as well. We can see that there are still 2 more bromines on this phosphorus. This process can repeat 2 more times. There's some acid-base chemistry that I'm not going to get into with it. So for our purposes in 201, if you're asked to push arrows for conversion of an alcohol, primary or secondary alcohol, to a primary or secondary alkyl bromide using phosphorus tribromide, this is what I expect you to be able to demonstrate. All right, let's now move on to seeing how to make alkyl chlorides with SOCl2. So similar to our reactions of alcohols with PBr3, right, you only need to know the reaction mechanism for alcohols and SOCl2 when it's a primary or secondary alcohol. Here once again, I'm going to go ahead and use that same secondary alcohol I used in our previous mechanism. And let's see how we can turn this into what the arrow pushing looks like to turn this into an alkyl chloride with SOCl2, also known as thionyl chloride. Now, sulfur is a pretty great atom. It's pretty big, right? We're going to be able to, once again, have our oxygen. Oop, got to have those electrons on chlorine, excuse me. Now, as I was saying, oxygen's once again going to act as a nucleophile. It's going to tack into this sulfur. Now, here we're not going to, this is not quite an SN2 step, right? But we're going to have one of those bonding pairs between the sulfur and oxygen and thionyl chloride is going to move on to that oxygen to generate our first intermediate. We still have our alcohol oxygen bonded to hydrogen. It is also now bonded to that sulfur atom of thionyl chloride. Here are our two chlorines. And finally, our oxygen from the sulfonyl chloride. And we can see now that in our first intermediate, we have a balanced charge. Positive on the alcohol oxygen, negative on the thionyl chloride oxygen. From there, lone pair from the thionyl chloride oxygen will reform that sulfur oxygen double bond, this time displacing chlorine from the sulfur to get to our second intermediates. Oxygen is still an oxonium. 3 bonds. We now have our sulfur bonded to one chlorine. And we have restored that double bond between the sulfur and the oxygen. To balance our charge, we have now generated a chlorine anion. And that's where our negative charge, so that we are overall neutral, remains. Here now, the next step is to deprotonate our oxonium. So I'm going to use pyridine this time. And lone pair on nitrogen will pick up that hydrogen and give us a overall 0 charge on our oxygen. From there, we now have this intermediate. We still have our protonated pyridine. Or excuse me, we have formed protonated pyridine. And we still have our chlorine anion. Make that a little bit bigger. Here now, our chlorine anion is going to attack SN2 at that electrophilic carbon of our alcohol. This is going to break our carbon-oxygen bond. These electrons are going to go bond to bond in our arrow pushing to form a new sulfur-oxygen double bond, which is going to displace the chlorine bonded to sulfur And now we can see how we form all three of the products from this reaction. We have our new alkyl chloride. Because we attacked in SN2 at that alcohol carbon, this alkyl chloride is formed with inversion of stereochemistry. When we form this sulfur-oxygen double bond and displace the chlorine bonded to sulfur, we form SO2. Let's make sure we get all of our electrons in here. There's for chlorine. There are for our SO2 oxygens. SO2 is a gas. And we still maintain that ion pair between our protonated weak base. Here now I'm using pyridine. You could use triethylamine, equally effective. And its counter ion is this displaced chlorine from sulfur. So that once again, we maintain overall charge balance through every step of our reaction. So here now is the arrow pushing that I expect you to know, right, for our conversion of primary and secondary alcohols to alkyl chlorides. All right, so the last thing we need to take a look at is for the Mitsunobu reaction. Now, the Mitsunobu reaction is the first truly complex reaction mechanism that we are going to see in Chem 201. This is so what we just did is a 1, 2, 3, 4-step mechanism. The Mitsunobu reaction is actually a 5-step mechanism, and there's a lot of moving parts going on there, but you will still be expected to know it for our class. So I'm going to clear this off, and we'll do the arrow pushing for the Mitsunobu reaction next. All right, so the Mitsunobu reaction. Now, recall, as we said in part 1, the Mitsunobu reaction is only for primary and secondary alcohols, right? We're never going to be able to do a Mitsunobu reaction on a tertiary alcohol. It must be primary or secondary. And we had 4 reagents in our Mitsunobu reaction. We had our primary or secondary alcohol. We had our weakly acidic nucleophile. We had triphenylphosphine, and we had dead. So the first step of the Mitsunobu reaction begins with dead and triphenylphosphine. So we're going to start off with dead. And I'm going to abbreviate triphenylphosphine as PPH3. This is an abbreviation I am perfectly comfortable using for you to use as well. I don't see really any point for you to draw out all 3 of those phenyl rings, right? They don't participate in the reaction, so we're not going to worry about drawing them. You can abbreviate it PPH3. You can abbreviate the ethyl groups on dead as ET if you choose to, which I will do after this first step for the rest of the mechanism. However, we do need to show, right, both of these carbamates, right? So the whole rest of this interior portion of dead, we do need to draw explicitly with all lone pairs and all bonds. And so in the first step of the Mitsunobu reaction, triphenylphosphine, the lone pair on phosphorus, attacks in to one of the nitrogen atoms, right? That is now going to displace this pi bonding pair. We're going to go bond to bond, which is going to displace the carbon-oxygen pi bonding pair. Here we're going to go bond to atom. This forms our first intermediate. So here now I'm going to go ahead and abbreviate my ethyl groups just as ET. We now have a double bond from that carbonyl carbon to nitrogen. Nitrogen still has a lone pair on it. We have a single bond to our other nitrogen, which still has a lone pair on it. That nitrogen is bonded to the phosphorus of triphenylphosphine. At this stage, phosphorus has 4 bonds and no lone pairs, so that means it must have a formal positive charge. That's good because it balances out that negative charge we had to put on oxygen. and here's the rest of dead. Now this intermediate, known as a betaene, has 4 possible resonance structures. While I am not going to draw them out here, you should draw these, try to find all 4 of these resonance structures that can be drawn, and be prepared to show them if you're asked to draw a arrow pushing mechanism for the Mitsunobu reaction. So 4 resonance structures for this intermediate, and you should be able to draw them all at this stage. From here, we now have our weakly acidic nucleophile is going to come into play. I'm just going to draw this as a generic. Let me clean that up a little bit for you. Right, I'm just going to draw this as a generic nucleophile, HNUC. And at this stage, what happens is that new lone pair we created on this oxygen is going to reform a pi bond to the carbonyl carbon. These electrons from the carbonyl carbon to this nitrogen are actually going to deprotonate our weakly acidic nucleophile, and we're going to generate our next step in the reaction mechanism. You'll notice that in all of the mechanisms I've drawn in this video lecture, and most all of the mechanisms we're going to see in Chem 201, we usually only have 2 to 3 arrows in any reaction step before we draw the product. Most of the reactions, we're going to have 2 electron arrows per step, but occasionally we will have 3 electron arrows per step, and we see that frequently in the Mitsunobu reaction. So the products of step 2, here now we have protonated dead at one of the nitrogens. So here we have ET. There's the oxygen atom to the ethyl group. We've reformed the carbon-oxygen double bond. Our carbonyl carbon is now single bonded to that nitrogen. And then nitrogen is what picks up. So this arrow here, where we deprotonate the nucleophile, the nitrogen actually ends up taking that hydrogen. Our other nitrogen is still bonded to triphenylphosphine. Excuse me. Phosphorus still has a positive charge, and the remainder of dead is untouched. We have a positive charge here that's no longer balanced by a negative charge in our intermediate, and that's okay because when we deprotonated our nucleophile, excuse me, I'm going to draw that in a slightly offset location. When we deprotonated our nucleophile, we left those electrons on the nucleophile, giving it now a negative charge, and so we're charged balance. At this stage, our primary or secondary alcohol can now participate in the reaction. So here now I'm drawing a secondary alcohol. This could also be a primary alcohol. And what that's going to do is it's going to go ahead, right? This oxygen is going to act as a nucleophile. It's going to attack into the phosphorus. It's going to break that phosphorus-nitrogen bond, which is going to go bond to bond, generate a pi bond between the nitrogen and the carbonyl carbon, which is going to force us to break a pi bond between the carbonyl carbon and that oxygen to put a lone pair on oxygen. Here now we can draw products of our third step, right? If we follow those arrows, here's one ethyl group on dead, to the oxygen to the carbonyl. Our nitrogen is still protonated, has a lone pair on it. Here now our other nitrogen, right, still has a lone pair on it, but now it is double bonded to that carbonyl oxygen. Sorry, the carbonyl carbon. The carbonyl oxygen now has 3 lone pairs and a negative charge. And there's our OET, which didn't really do much for us. Right? So here now we have a negative charge. Let's take a look at what happened between our alcohol and triphenylphosphine. So we have, there's one of our R groups on the secondary alcohol, there's our other R group on the secondary alcohol. Our oxygen from that alcohol is now bonded to phosphorus. We see that phosphorus has 4 bonds, no lone pair. It maintains a positive charge. That oxygen atom still has a hydrogen attached to it and 1 lone pair. So it also takes a positive charge. Now the last thing we need is to balance out those charges, and that is balanced by our nucleophile that has a lone pair and our negative charge. All right, so that's the products of the arrows in step 3. In step 4, this new lone pair on the carbonyl oxygen in dead is going to come down to regenerate our carbon-oxygen pi bond. We're going to take our electrons in our carbon-nitrogen pi bond, and those are going to deprotonate, right, this oxonium. The electrons from that oxygen-hydrogen bond are now going to go back to oxygen. And so this is now step 3. I'd like to highlight, though, that this intermediate here, right, has 2 possible resonance structures. And you're going to need to know the 2 possible resonance structures that it can form before we do the arrow pushing in step 4. So after the arrow pushing in step 4, right, dead is now done with its job. And so we're just going to draw it off to the side because it's no longer going to participate in the reaction. So what it looks like once the job is all done, there's our ETO on one side. There's our carbonyl for that side. Here's our nitrogen that's protonated with a lone pair, single bonded to another nitrogen which is protonated with a lone pair, to our other carbonyl and our other O ethyl group. So that takes care of dead. It's done. It's not going to do anything else for us in the reaction. Right? If we draw the products of what happened with our oxygen phosphorus new compound that we have here, or intermediate I should say that we have here, we still have both of our R groups attached to that alcohol oxygen. It's now been deprotonated, so it has 2 lone pairs. It's still bonded to the phosphorus, which still has the 3 phenyl groups on it. Phosphorus still has 4 bonds, no lone pair. It has a positive charge. I'm going to highlight here that this intermediate has 2 possible resonance structures, and you should be able to draw them both. We also still have our nucleophile with its lone pair and negative charge, and so we are maintaining the fact that we stay neutral all the way through every step. Here now we are in our final and 5th step of arrow pushing. And in this step, our nucleophile attacks this alcohol carbon SN2. Let me go ahead and clean up that arrow so it's nice and clear. All right, so now our nucleophile is going to go ahead and attack SN2 into our electrophilic carbon of our alcohol. That's going to go ahead, break that carbon-oxygen bond. That pair of electrons is going to go bond to form an oxygen-phosphorus double bond, right? And we get our last 2 products, or our product and our last byproduct of the reaction, right? We now have, because this is an SN2 process, we have now our substituted alcohol, which forms with inversion, and we have also formed triphenylphosphine oxide. Right? Phosphorus now has 5 bonds, and if we recall from video lecture on bonding, phosphorus can accommodate 5 bonds and remain neutral thanks to its d orbitals. Okay, this is the arrow pushing for the Mitsunobu reaction. We start off with dead triphenylphosphine, go to form our beta-ene, which has 4 resonance structures. Our beta-ene deprotonates our weakly acidic nucleophile, at which point we come now to this intermediate. Our alcohol can attack into phosphorus at this point, generates this, which breaks our phosphorus-nitrogen bond, generates this new intermediate from dead, which has 2 resonance structures we need to know. That new dead intermediate that's negatively charged can deprotonate our new oxygen-phosphorus intermediate. From there, dead is now done with its role in the reaction. Our nucleophile can come and attack SN2 into our positively charged phosphorus-oxygen compound, which results in our substituted alcohol produced with inversion of stereochemistry. Triphenylphosphine is our byproduct. And so, just to be clear, I'm going to go ahead and box our 2 byproducts, triphenylphosphine oxide, and here is our byproduct from dead. All right, so that covers all of the arrow pushing for topic 15. All of the reaction mechanisms that you have seen in this video lecture are fair game for exam 2. Which one I'm going to choose, haven't decided yet, but any one of these or the SN1 mechanisms or the SN2 mechanisms are all fair game. And I'll tell you right now, page 3 of exam 2 will be one single arrow pushing mechanism that you must complete start to finish. All right, thank you very much. I hope you've enjoyed both of the video lectures, or at least felt that the video lectures for topic 15 have been informative. And if you have any questions, please feel free to bring them up in lecture, conference, or stop by for office hours. Have a good one.